So this is really a, please ask questions if you want this. So just cover a few general topics which you have to consider. But I'm not going to cover everything that can be done. But just if you don't, and there aren't 37 slides. There's some of them are not relevant here. I've hidden some of them because they're not relevant in this talk. So so I'm going to very briefly talk about what's just A. Sorry, I didn't. I think, Michael, I didn't quite. Is that a question? Sorry to be. Okay, fine. So we can divide. No problem. We can divide up overheads into four main categories. So when this is talking about optimizing. You've got an MPI program, and it isn't running as fast as you think it would. What are the issues? So the overheads that make a parallel program go slower, typically you can be classified into four ways. Lack of parallelism, and this is Amdahl's law. Amdahl's law says that the speed up you attain by any parallel program is entirely limited by the serial part. If your program runs for 10 seconds and spends 1 second in a serial part, maybe doing I/O, doesn't matter how many processes you run on, you're still going to have that 1 second overhead. So if you're spending 10% of your program in serial code, then there's no way that you can run more than 10 times as fast, no matter how many processes you run on. Load imbalance is that processes do different amounts of work, and the important point is that typically gets worse as you run on more processes, and so in effect gets worse. And then I'll spend most of my time talking about synchronization and communication, and how to use MPI to try and minimize those overheads. But I mean, the lack of parallelism is tasks may be idle because only a subset of tasks are computing. It could be worked on task 0 or task 0 of every communicator. I mean, really, this is very difficult. The only cure is to redesign the algorithm to exploit more parallelism. So, when you first write a program, you may say, this calculation is difficult to do in parallel. I'll just do it on a single process and broadcast the results, or redundantly compute it, have every process do the same computation. You really need to redesign the algorithm to exploit more parallelism. So I'm not really going to talk about that here, although I'm going to talk about how bad it can be. The classic one is I/O. I mean, the standard way, your first port of call for doing I/O is to collect all the data onto a single process, say process 0, rank 0, for rank 0 to write out all the data. That is not scalable for a whole bunch of reasons. And so, if parallel I/O is your limitation, you want to look at MPI+/IO or other libraries like HDF5, which are also parallel, or a more modern one called Adios. But parallel I/O does have solutions to somewhat reduce that. Otherwise, you're going to have to look at redesigning your algorithm. But I mean, you might. The important point is that Amdahl's law assumes that the serial section, this overhead, is constant as you increase the number of processes. But actually, often you can actually get a piece of code which you do in serial, which scales as the number of processes. The more processes there are, the more work there is to do. So this is so let's assume a code is perfectly parallel except for a small part which scales as order p. That means that the small serial part, this is relating to an example you haven't done yet, actually. It's from another course. But we've got a piece of code which takes order the number of processes to implement. That could be sending a message to every process linearly or something like that. So the time taken for the parallel code, this is just a modification of Amdahl's law. Alpha is the percentage of serial code. So Amdahl's law with the parallel times is the sequential time times the fraction which is parallel divided by the number of processes plus a constant. But here we're saying, imagine that there isn't a constant overhead, that overhead scales with the number of processes. And there's lots of times you can think of naive approaches which do that. Okay. What does that look like? Well, we've got some graphs here, and so Amdahl's law is 1 minus a over p. This is this parallel part scaling perfectly, time decreasing with the number of processes, plus a constant overhead. Okay. What happens if that overhead scales with the number of processes? Okay. So if we take a equals 0.0001, that's saying that your code is 99.99% parallel. Yeah. 99.99% parallel, one part in 10,000 serial. For 1,000 processes, Amdahl's law gives a speed up of 900. That's saying it's good. But if the overhead scale the number of processes, the maximum speed up is order 50. So that's showing that, you know, if you have Amdahl's law is often used as a way of saying, you know, this is a real problem. It can limit the scalability of your code. In practice, it can be even worse than that, because you may have an overhead which isn't constant but scales with the number of processes. I/O might be a standard one there. If everybody sends their data to a controller process who writes it out one by one, that will take order, you know, that will scale with the number of processes. So, you know, it is a problem. I've got some graphs here which were done by a colleague of mine in Wolfram Alpha, which don't necessarily, they're going to come up in another, they're going to come up in a different window, which is going to be something of an issue. Why don't I'll only show you one of them. So, well, okay, I'll show you these two. Okay, so basically, this is the speed up you get with Amdahl's law. So the scaling is not very good on this, but you'll see that you know, it scales, and then it will peak because the serial fraction is 1 part in 10,000. It can never get faster than 10,000 times faster, but it is getting quite a bit faster, and it never gets slower. That's the important point. Amdahl's law predicts that a code never gets slower. However, if we were to use a term which scaled with the number of processes, you'll see that we get a scale of 50 at 100 processes, then it goes off completely. So, you know, although Amdahl's law looks like a worst case scenario, it's far from the worst case scenario. It actually, you know, you can get things that are worse than that. And actually, the scalability of a global sum, a parallel algorithm, as we talked about in the previous lecture, goes as log the number of processes. So what happens if we have an overhead which isn't constant, doesn't scale with the number of processes, but scales as the logarithm of the number of processes, which is true for a lot of collective operations? Then you would get a graph which looks like this, which isn't quite so bad, but still isn't brilliant. Okay, you're getting a scalability which stops at, you know, it peaks at well under 1,000 when Amdahl's law would predict it get up to 10,000. So, you know, in reality, the overheads can be much worse than Amdahl's law predicts, and so that is a problem. One of the classic ways to alleviate that, for example, for global sums, is just to do them less often. But anyway, we'll come back to that later. So that was, apologies, these graphs don't look particularly good, but they illustrate the point. There's more here that you can generate if you want, but then actually, you know, things can be a lot worse than Amdahl's law. But you just have to use a different algorithm, and then, you know, that's a whole different ball game in itself. But you should not be doing things like sending messages linearly to lots of processes. You should do that with a collective. I/O you should do in parallel, which requires some work. The other reason for lack of scalability, especially at high core counts, is load imbalance. All tasks have some work to do, but some more than others. This is a much harder problem to solve in message passing. In the shared variables model, OpenMP, on a node, there are two. We have inbuilt techniques in OpenMP for doing dynamic load balance. If you've done OpenMP, OMP parallel 4 or parallel do with a dynamic schedule, will automatically do load balancing. And the reason is, on a node in a single computer, you have a shared memory. And so all the data is accessible to all the threads, to all the CPU cores. So if you have a task you want to process a thread to do, you just tell that thread to do that task. However, in message passing, in distributed memory, the problem is to give a new process a task to do, you also have to send them the data. And so there's a huge overhead to doing dynamic load balancing. You need to move the data explicitly to where the task will execute. This may require a lot of algorithmic changes. And actually, the load balancing algorithms may take twice as long for twice as many processes. So actually, load balancing itself can be very expensive. So this is very difficult to achieve, especially if it's dynamic. If it's static, if you have a static setup, like simulating the weather across the UK or the currents of the oceans, then there are techniques for dividing a grid up into equal sized pieces, which work quite well. But if there's anything dynamic in load and it is very difficult to do it in message passing. So what we're going to look at now is where we see time being spent. How do we find out where the time is being spent in our parallel program? Well, we could just put explicit timing calls around all our message passing calls using MPI time, which gives you the raw clock time. But probably the easier thing to do is to use profiling tools. And there are a number of profiling tools available. On ARCHER2, we have something called a Cray product. We have a Cray product called a CrayPad, Cray Performance Analysis Tool, I think. But in general, there's a portable one, an open source, which is called Scalability, and we ran a course on that recently. So if you do want to find out where your program is spending its time, you know, a good first stop would be to look at the Scalability tool, which will report that kind of stuff. However, you do need to be these tracing tools actually show up load imbalance very clearly, because typically what happens if you have load imbalance is you'll have lots of processes doing some work, and they'll be sending messages to each other. If a process has not very much work to do, it will finish quickly and it will be waiting. Another process will be slow. So in fact, typically, load imbalance, if you use a profiling tool, shows up as a lot of time spent in blocking routines, such as receives or collectives. We'll come back to that. But load imbalance, if you run a profiling tool, you will detect load imbalance by seeing an awful lot of time in MPI routines which shouldn't take much time at all. And that's because the receive isn't actually taking much time. You're issuing the receive and you're having to wait for a long time for a very slow process to send you the data. So the receive is taking a lot of time, but it's all waiting around. It's all synchronization, no communication. So tracing tools show up load imbalance very clearly. However, tracing tools have an overhead to them, and they can be difficult to use on very large codes for very large runtimes or very large core counts. But they are a very good way of detecting load imbalance, not curing it, but detecting it. But synchronization is where you spend, where you lose time in MPI, because synchronization is coupled to communication. You get it with blocking sends and receives. Any non-blocking send or receive, you still have to wait on it to complete, and that's a synchronization. And collective comms are almost all synchronizing. The classic one being an all reduce. Everyone has to participate in the all reduce. So if one process arrives early, it has to, sorry, if one process is slow, all the other processes have to wait for it. Just a bit of a aside here. If I were to tell you the number one optimization technique for optimizing an MPI code, it would be take out all the MPI barriers. MPI barrier is almost never required for correctness. People seem to put it in all the time. I mean, you can come up with, you can engineer MPI programs which are correct with barriers in them and incorrect otherwise, but they have to be quite contrived. So, you know, really think very carefully while you're using MPI barriers. Very useful for timing. If you're timing a code, you need barriers to make sure everyone starts at the same time. But, you know, really think carefully while you're using it. But the important point is that you might say, well, I'm not going to have any synchronization overheads in my program because it's perfectly load balanced. So all the processes are running at the same rate. So when one process is sending, the other one is receiving. The problem is that on modern computers are very complicated. And basically, although you think the processes are running at the same speed, they're probably not for a whole bunch of reasons. But the classic one is operating system interrupts. Every now and again, the operating system has to do something, even on a supercomputer where the OS will have been stripped down to its minimum. And the operating system has to run somewhere, has to run on a CPU core. That will slow down that CPU core, and that rank will then run slower. And then that means they're running at different speeds, and whenever you synchronize, you waste time. So basically, synchronization can, especially if the synchronization is unnecessary, can amplify random noise effects, e.g. OS interrupts. And so this was an effect which only became discovered when machines got very large, but you need to be aware that although you'd like to think your MPI processes are running at the same speed, they aren't necessarily doing so for a whole bunch of reasons. But let's look at very simple communications. Let's look at point-to-point and collective. Where can the overheads arise in these calls? So we've talked about this. We measured it. Small point-to-point communications typically incur a startup cost. Even sending 0 bytes takes a finite time. So if we think the time to send a message is the latency plus the number of bytes times the time per byte, we saw that, well, actually, we normally quote this as the time is the latency plus the number of bytes divided by the bandwidth. And so we saw the latency was measured in microseconds, the bandwidth in gigabytes, if not tens of gigabytes per second. But the important thing here is it shows you that sending any message is expensive. It's faster to send one large message versus many small ones. So this is the #1 optimization in MPI. You should send one large message versus many small ones. So for example, if you have 2 doubles to add up, you should do 1 OR reduce of 2 doubles versus 2 OR reduces of 1 double. You might say, well, I have a mixed data type. I have a data type which has floats and integers. I can't send them with a single message because they're different data types. And remember, a single MPI send only takes a single data type. Well, the trick there is to use derived data types. There are derived data types for structures and such like, which can be used to send messages with a mix of types. So, but that is the #1 MPI optimization. The very first MPI optimization is to use collectives where they exist. The next one is to always use a small number of large messages versus a large number of small ones. And that is really the most important message. So, but load imbalance and wasted time synchronization costs can show up, and there are names for these communication patterns. And this is nothing to do with OO design. I really mean physical, how the ranks are communicating with each other. And it can be useful to think of these because they will pick up some of these, and you can use the right words for them. You speak to somebody else. You can identify them by I. Some of the tools like Scholastica actually try and say, it looks to me like your code is suffering from this problem, okay, because it may have detected a lot of time spent in receive. And so sometimes you can do it by I. Some tools like Scholastica have sort of clever systems which look at the try and spot these for you. But the classic one, for example, is late sender. Okay, so this is time going from left to right. We have one process issuing a receive. It issues it here, but the receive cannot complete because the send hasn't been sent yet. So this receiver is blocked in the receive until the send is coming. So this guy's waiting in the receive until this process sends us the data. So a late send is if a blocking receive is posted before a matching send, then the receiving task must wait until the data is sent. And actually some tools, CRAPAT being one of them, will split communication time into 2 pieces. One is the time actually to send the message, which is this time here, but the synchronization time. So again, in a tool like CRAPAT, or you can get hold of such a tool for your system, where it can differentiate between synchronization and actual data transfer, that would be a very quick way of seeing you have these problems. Okay. Out of order receives is a similar problem. So now we have 3 processes, 1, 2, and 3. And this third process is receiving data from the other 2. What it does is it issues the receive from this first process first. So it's sitting there and waiting till that comes in. But it turns out that the first send was issued by this process. Okay. So for example, this receive has to wait for that send, and also this send, if it's done synchronously, has to wait for that receive. So what you've got here is the sends are happening in one order, and you're issuing the receives in the other order. And you can imagine real situations where this is true. In a standard 3D domain decomposition code, you have 6 sends and 6 receives. So you have 6 messages coming in and 6 going out. So late senders may be the result of having blocking receives in the wrong order. Now, if this is really your situation, you could switch the receives around. Okay, so I'll receive from rank this process before this one, and that will mean that things will go quicker. Unfortunately, it's very rare that this is as simple as this. Normally, this outer orderness is caused because of random fluctuations. What I mean is that this process was just slow for some reason, or this one was very fast for some random reason which isn't reproducible. And this is especially true on multi-core processors, where all CPU cores on a process contend for resources, share resources, and the execution speed is quite unpredictable. So you'd like to think that you've got a program where this process sends first and this one sends second, therefore this receive should be first and this receive should be second, but that could often happen in an unpredictable way. Late receiver is actually so late sender means the receiver is delayed. Late receiver happens when you've got synchronous send, and the late receiver is when you issue a late receive and the sender is delayed. If send is synchronous, which is likely to be true for large messages, data cannot be sent until the receive is posted. Okay, so this is either explicitly programmed. So what I mean is you may have used explicitly used synchronous send, or this may be an MPI send, which is synchronous because of the size of the message, and the sending task here is delayed. It cannot complete the send until the receive is posted. So we're going to think about ways to get around this situation, and the main way of getting around this is not to impose an order, not to receive from one process then another, but to receive them all at the same time, which is actually what non-blocking communications are used for or useful for. The reason that this is a problem is that you are imposing an order on the receives, but you don't know what that order will be because you don't know what order the sends are coming in. And so you should really use non-blocking communications. But there is a final case here which I put in because it's not obvious, but it's a real effect. And it comes about because you probably think of MPI as running continuously. You think of MPI as being a universal postmaster running in the background, processing messages. And I've already mentioned that's probably not true. But in this view of the world, you think of asynchronous and non-blocking communications happening in the background. You ask MPI to do something, it will carry on doing that while you do something else, while your main process does something else. And if you think about that, you think it's obvious that you should be able to overlap communications and calculation in time. To say to MPI, please send this message. While you're sending it, I'll go back and do some calculation, and later on I'll come back and see whether you finished or not. This is not generally true. MPI is single-threaded by default, i.e. MPI can only run when you're actually calling the MPI library. Communication can only be processed when your program calls an MPI function. As I mentioned before, MPI treats any call to its library as kind of a manual interrupt. The first time, whenever you call MPI, it says, great, thanks for calling me. I can go and do some bookkeeping, some housekeeping operations, matching out sends and receives. It'll do all that stuff before it ever actually goes and doing what you asked it to do. So if you issue a non-blocking send and then have a wait, your mental model might be that non-blocking send happens in the background continuously until the wait. That's probably not true. It will probably either be sent immediately if there's an existing receive, or if not, it will be queued up to be sent later, and it cannot be sent until the next explicit MPI call, which could be a call unrelated to the outstanding communication, but it cannot. If you issue a non-blocking send to a process and it's not ready for it, that will not be able to be sent until some other explicit MPI call. And this gives a slightly subtle effect, which is quite difficult, which is a bit like late receiver, but it's when you do non-blocking sends. So what happens is here, you issue a non-blocking send, okay, and the receive hasn't been posted yet. And so all that happens is inside the MPI library on this process, that's queued up as a send. You basically set up this, you say, look, I want to send you some data, but you weren't ready. Control then returns to your main program, and that data cannot be transferred until you next call the MPI library. Now, the next call may be unrelated to this. This could be a receive for a different message, but as soon as you call the receive, MPI goes, oh, wait a second, there was this outstanding send. Is this guy ready to receive? Yes, they are, and I can send the data. So that means that the receiving process is delayed, even though there was an outstanding send, non-blocking send, because that outstanding non-blocking send cannot be processed until this rank re-enters the MPI library. So the non-blocking implementation not yet sent the data. It may copy it into an internal buffer, it depends on the implementation. and the actual send is delayed until the MPI library is re-entered by the sender. And that can be quite difficult to diagnose because the data transfer will happen in a place which you don't expect. But the basic cure to this is to have as many MPI operations ongoing at the same time as possible and not to impose an order on them. And that is the basic solution there, is to use non-blocking communications. So, in principle, you could avoid these late senders and receivers by careful ordering, but the problem is the ordering is probably random. So there's a whole bunch of network congestion or whatever. Not all tasks at the same time to do the same computation. Not all messages of the same length take the same time to arrive because of possibly network congestion. So the thing you should do is to avoid delays by using all non-blocking communications entirely. Use iSends, iReceives, and then await all. So what you do is you post in a 3D halo swapping code, you post 12 communications, send up, down, left, right, forward, backwards. You post receive up, down, left, right, forward, backwards. And then you say to MPI, go into the MPI library and just wait for all of these to finish. And then MPI can deal with them as and when they're ready. It's also advantageous to post the receives as early as possible, because as we said, if the receives are posted, okay, then this could have completed right at the start rather than having to wait. So, basically, what you would do for halo swapping, this is a 2D, just a 1D example, but you loop many times, post the iReceive, post the iSend, and then wait for them to complete. You might be tempted to try and overlap communications and calculation. So often you can say, I post my sends and receives, I update some core of the array where that calculation does not depend on the halos, then I wait, and then I do the calculation involving halos. That may or may not be advantageous. It might be, it might not. It's hard to know without programming it. But a lot of people, in their codes, put a lot of effort to try and overlap communications and calculation. All I would say is that may work, but you should be always very careful to maintain a version of your code which doesn't overlap communications and calculation, a more naive version which could actually be faster. This is just receive not. You might think that your receives are posted before your sends, but then they're not really, because you want someone else's receives. And that's a slightly subtle point. But then sometimes you can post the receives quite early. You might be able to do it. You should post the receives as early as you can, and that might be actually at the end of this loop rather than the start of the next one. But it very much depends on the structure of your code. We get similar patterns for collectives, like we do for point to point. Apologies. So, for example, if you're doing a broadcast, if one of the processes, so this is a classic situation which you'll see, and the classic model you might have at the start of a code is if I'm rank 0 reading the data, then broadcast it to everybody. So what happens is that everybody except for rank 0 isn't reading in the data, so they go into the broadcast straight away, but they wait for a long time till, in this region here, rank 0 is doing the I/O, reading it from a file, and then it can broadcast the data. Now, in that case, there's not really much you can do other than use genuine parallel I/O. But you need to be careful. Again, if you run a profiling tool and it says you're spending a lot of time in collective communications, it can often be a sign of load imbalance. But in a broadcast, if the route is late, all of the tasks have to wait, and that also applies to scatter and scatter-v, which are another ways of distributing data. Similarly for gather or for early reduce, if you're doing a reduce, if the root task of the reduce is early, it has to wait for all the other tasks to enter the reduce. And the same for a gather operation. In practice, they can be difficult to fix, and often they're not so much of a problem because these are maybe only at startup and shutdown of your program. However, if you do have a program which does lots of gathers or reduces in the inside, again, this is typically a symptom of load imbalance, and if you saw a lot of time being spent here, you'd have to fix load imbalance first. Another all-to-all, this is a classic pattern you do in parallel FFTs. It's a global transpose of a matrix. Every process communicates with every other one. And again, if they're not all called at the same time, if somebody calls it early, this process here just has to wait for everyone to call the routine. Other collectors require all the tasks to arrive before any can leave, and that's all reduce and all to all of the classic ones here. So collectives are hopefully well optimized for the architecture. It's one of the few times, the MPI manual is not particularly readable, but it is one of the few times I would recommend looking at the MPI manual is to have a look at what collectives are available, because that is the easiest way to optimize your code. Don't program something up yourself, program it up using collectives. Now, you may look at the manual and decide that the collective operation isn't quite what you need. Well, there are tricks you can use, and that's the subject of the last lecture today, to say, look, you can sometimes shoehorn the collective into doing what you want if you understand the way that data types work. However, they are expensive. They're an overhead which isn't present in the serial program. Help to reduce their use as far as possible. So, for example, often you may be doing an optimization problem. There's some error value you want to stop on when the global error value is less than 10 to the minus 3. You're tempted to check that every iteration, but that could be very expensive. So it might actually be worthwhile checking every 10 or 100 iterations. Yes, you might do 9 or 99 more iterations than you need to, but if you're doing a lot of iterations and the overhead of checking is high, then it may be beneficial to reduce the frequency of checking for convergence compared to the sequential algorithm. People often say, why can't I use non-blocking collectives? The problem is they just don't seem to work. I think they're a lot more difficult to implement efficiently. So they may not actually happen, not asynchronously. I have rarely found a use for non-blocking collectives. Again, you can think of many in principle use cases, but in practice, I have yet to see a convincing argument for them being faster. So I think the main message from this talk is use collectors where you can, send a small number of large messages, not a large number of small messages. Try and fix load imbalance, but whenever you do communications, use all non-blocking communications. The reason I mention that is a lot of people learn MPI send receive and do all their communications with send receive. Send receive is imposing an ordering. You're saying, I'm going to send to that process and receive that process, but maybe another process is ready for you. Okay, and you do not impose unnecessary orderings. Use all fully non-blocking communications. And the exercise here, so yeah, to summarize, lack of parallelism requires you to redesign your algorithm. Load imbalance can be difficult to fix, but relatively easy to spot. Synchronization is processes waiting for each other. In that case, use non-blocking communications if you can. And inefficient patterns of communication, but try and use collectives where you can. So the exercise for this is slightly, if I share, it's quite a simple exercise. It is a what I've written is for other purposes actually I wrote a halo swapping routine, and what it is a halo swapping benchmark. It basically does halo swaps in a whole bunch of different ways, and it's on. So the instructions are at the bottom here. There we go. So description of 3D halo swapping is in this README. So if I go there, separate, you'll see that what it does is it sets up a 3D array of processes and swaps halos up and down in all 3 directions. And it implements a lot of these things, so you can see whether they're beneficial. So the first thing it does pairwise swapping each turn using send receive, and there you might imagine that you would suffer from late sender or late receiver because you're imposing a deadlock, an ordering. Another similar technique that people do to avoid deadlock is they split the processes into odd and even pairs, and I call them red and black. The red process send first and receive second. The black do the opposite. This is similar to this approach. Then we can start using non-blocking, but we can do it in turn in each dimension using I send, receive, and wait. You might say, I'm going to do a non-blocking receive, so I receive, send, and wait, or each dimension in turn using I send, I receive, and wait all. So you say, I want to send to my up process, receive from my up process, and wait. However, from what I've said, you would expect this to be the best. Issue all the communications, all the sets, so receive up, receive down, receive left, receive right, receive forward, receive backwards, the same 6 for the sends, and then wait for everything. So those are the options, and I would expect this to be the fastest. I have also implemented persistent communications and neighborhood collectors, which you would look at, but I don't. They typically they aren't any faster than this, but they're in there if you want to have a look at them. So if I just get let's look at what we're supposed to do. I will now share my window. So that's my Archer window, Archer2 window. I can, whoops. Okay, it doesn't seem to want to cut and paste that. Give me a second. Why it didn't want to, there we go. So that's my Halo bench. We go into Halo bench. It's in Fortran. This is for historical reasons. As I said, I don't have a C version of this. I've just, but we should be able to make from Makefile Archer2. So that compiles. If you want to look at the code, although it's in Fortran, it's very simple MPI. So you should be able to sight read it even if you're not a Fortran programmer. So basically, what it does, it has 8 Halo tests, as you'll see here. It, by default, the messages are 10,000 bytes, 10,000 items, where the items are actually double precision. Where do we actually allocate them? I think they're doubles. I should know that actually. So send off. Yes, the double precision. So these messages are 80K long. That's just below the eager limit. So that would be interesting to try a different number there. But if you'll see, it just loops over in this order. It uses the send, receive, red, black, pairwise non-blocking, either the send, non-blocking, the receive, or both. Then the thing which, according to the previous talk, should be the best. And then it does these other ones, and all it does is it just loops over, does some printing, and it just basically loops over them and says, it calls them with various names, and this is called Halo swap.f90. I'll just show you 2 of them. Okay, this is the Halo send receive implementation. And what it does, okay, it's very simple. It loops over a number of repetitions. We have to do lots of repetitions to get a measurable time. Loops over the dimensions, which is 1, 2, and 3, because we're on a 3D grid. It loops over the directions, which is up and down, and it calls a send receive for it. So this calls 3 times 2 send receives, i.e. 6 send receives, and okay. The non-blocking one does where are we? This is it here. I receive, I send, wait all. I've called it, rather long name. But what it does is it basically it loops over. This is basically whether you're doing sends or receives. Loops over send and receive which is 2. It loops over the dimensions, then it loops over the directions. So this is going to issue 6 receives and 6 sends. Okay, so it basically loops over, and then non-blocking, so it'll issue them all, stores them in a little array, and at the end, so this is just initializing the communications. Okay, they actually happen at the wait all. And if you're interested, I do have these. I do have the. This looks very similar for the persistent, but this loop over all the things doesn't actually perform the communication. It just sets them up. It says to MPI, look, I'm going to be doing lots of these and lots of these, and here I have to be careful about the tag for reasons I mentioned before. Persistent communications don't respect message ordering, so I need to tag them. That's a bit of a subtlety. But we have a setup loop which we issue once or 12 times, but we basically do the communications many times. This is thousands and thousands of times. So we say start all the communications and wait for them all to complete. So that's sort of doing the same, effectively doing the same as the non-blocking, all non-blocking, but just doing them in a different way. So if you look at this is not set to run in the reservation. The reason is that I want to run it on 8 nodes. I just want to have a reasonable number of nodes, and so that's not going to run the reservation. You could run it in the reservation, but the reservation is a maximum of 4 nodes. But this, I should be able to sbatch archer2.job, archer2.job. Hopefully that works. Okay. Is it running? It's running. So this is going to the short queue. So we have 4 nodes reserved for the exercises. You can guarantee to get a job round instantaneously in 4. On more than 4, we need to submit to the short queue, which can take you up to 16 nodes, I think. But it's running pretty quick, and that will run pretty quickly. Hopefully. Maybe it shouldn't take more than a couple of minutes to run at the most, I don't think. Just check that it's running okay. Oops. I can't get cut and paste to work in Windows. Okay, as finished. Okay, fine. So it produces figures. You can look at them. But what I also wanted to do was, it's interesting because we saw that the eager limit was somewhere around a few hundred kilobytes. So if I make that n buff is 100,000, and that means that's 800 kilobytes and reduce the number of repetitions, I can submit that one. Sorry. So, you know, I'll let you play around with those. What I'll do is I'll review the results of those at the beginning of the so the practical session. I mean, you can carry on doing the ping pong if you want, or running this example. The practical session is now till 3:30. Then we've got a tea break until 3. So I'll review these results at the beginning of. So I'll just put a message up here. If there are any questions, I didn't see any chat messages coming in. No. This is quite a short lecture, the advanced collectors. It's probably half an hour at the most, if not. But we'll do a practical session until 15:30. I'll be here to answer. I hope it. Please tell me if you have any problems compiling and running that. I'll review the results at 4 and then do the final lecture of the day. So please, I'm also happy to answer questions you have about your own code, more than happy to do that in this practical session. I mean, I'm here for the next half hour at least. If you have any question you have about your own program you'd like to ask, we can go into a screen sharing and I can look at your code. It's really up to you.